Hello, class. I'm going to do a recording for Chapter 8, Section 1. It's called the real number line and absolute value. Okay. And this is for the Math for 10 course. Okay. Not for the COREC, but for the Math for 10. Okay. All right. So let's start with, okay. So remember, with this page 17 that you want to do the learn part and spend about 15 minutes in the learn. I have a teacher's edition, so these are already kind of filled in, but yours is blank. Your page is blank. So you want to go through the learn and they will help you fill this out as you go through that. And it is like something that you would see in the ebook. Not all of the ebook content is in this workbook. And so that's why I refer you to the ebook, the textbook, because you can see like actual worked out problems as well, other examples. But the ebook does not have any live video in it. So it's just reading from the ebook and it's reading extra examples. But your learn does have, it's full of videos. And anytime you see this, there's like a little video. And so you should be able to see that as you progress through your learn. And you should take a look at that. Okay. And then, so I'm going to start with the bottom part of 18. So you can go to the bottom part of 18. And again, this is important, so you're going to go through this. I'm expecting you to go through this in the learn, okay? But I start with 8.1 here. Okay, and it says that on a number line, smaller numbers are always to the left of large numbers. And this is like a true or false statement. And this is a true statement. That is true with what they're saying. If I give you an example, draw an example, number line. And if I put 0 here, 1, 2, -1, -2, -3. And if I'm comparing these two numbers, let's say I compare the -3 and the -2. And -3 is being compared with -2. Okay, so according to the statement, it says smaller numbers are always going to be to the left of larger numbers. So that means that -3 would be smaller because it's to the left of this -2. Okay, so -3 is less than -2, and that's the symbol for less than. Okay, and sometimes they say if you want to, sometimes people forget the symbols less than, greater than. If you draw like a Pac-Man around that, a little tooth on them, in gaming, you win by consuming large numbers, right? The person with the most points wins. So, this little Pac-Man is gonna, when this is drawn, he wants to consume the -2 because -2 has more value. Okay. And so that's another way to remember the symbols, because sometimes people forget less than or greater than. Okay. If I also compare the number 2 with the number -1, okay, so let me change ink. So 2 is right here, and -1 is right here. Okay. So according to this, smaller numbers are always to the left of larger numbers. So -1 is going to be smaller. 2 is going to be larger. Okay. But when you compare this, when you compare inequalities, you always want to compare it from left to right. So this number on the is what in comparison to -1? Well, 2 is greater than. Two is greater than -1. And the symbol for greater than, this is the symbol for greater than. Again, if you think about drawing a Pac-Man around that, put a little tooth here. See, he's going to consume the bigger number. He's going to consume the 2. 2 is worth more points than a -1. Okay. All right. Okay, problem number 2 says the absolute value of a negative number is going to be a positive number. And that's true. If I ask about the absolute value of -2, that's just going to be 2. Okay. And so the picture for that would look like this. And you always have 0 for orientation, and then you have -2. Let's say -2 is out here. Let's say here you are. Okay, and you've got like a measuring tape, and you extend your measuring tape or your ruler out this way. Okay, so you know the directions north, south, east, west. So you're heading west in the negative direction. But when you look at your ruler, and I have a ruler here, nobody's rulers, even if you have a seamstress with a soft type of ruler for measuring, you know, the width of arms and things like that, or if you have like a carpenter's ruler, like the stainless steel type of rulers, nobody's ruler has negative numbers on them. Those, because you're measuring distance. And that's what absolute value does. It measures distance on the number line from 0. So you have your measuring tape extended out in the west direction, but when you look at how long it is, the distance, that's going to just be recorded as 2 units of length. Okay, so that's true. The absolute value of a negative number is +2. That's true. Okay. So absolute value measures distance from 0. Okay, measures distance from 0. Okay. Also, continuing to talk about absolute value. If I ask for the absolute value of just 2, that would just be 2 as well. The absolute value of 2 means you have this number line, and here's 0 and 2's over here. And here you are at 0, measuring distance from 0, and you come out this way. So you come out the east direction, moving east. And when you look at the length and you extend your ruler out, how long is that from 0 to 2? That's just, you know, 2 units of length. So the absolute value of 2 is just 2. Okay. So you're measuring distance. So distance is not negative. The only way that a problem could be set up where you end up having a negative answer for absolute value is only if you have a negative outside of the absolute value bars. So like if I were to take this problem here, this absolute value of -2, but I put a negative, see, outside, then that would end up being -2, because this means like take the opposite. It also means multiply by -1. Multiply by -1. That's also what that means. Okay. And so, so yeah, so you know from here that the absolute value of -2 was 2. So if you multiply 2 times -1, that would give you -2. Also, if we say, okay, what if you take the opposite? What if you take the opposite of 2? The opposite of 2 is -2. Okay, so I would say the only way that something with an absolute value could end up being negative in your answer is if it's got the little negative on the outside of the absolute value bars. Okay. If I also, thinking about this problem, if I also write that up here, but then I put a negative outside. So this is, take the opposite of the absolute value of 2. Okay, then that would equal -2. Okay. So you got the negative on the outside of those absolute value bars. Okay, then at the bottom it says that all whole numbers are also integers. And that is true. So whole numbers, now there is some a vocabulary sheet. Let's see, where did I put that? You can use me on your quiz. Let's see. So we can find this. So it's going to be kind of hard to explain because it doesn't have a page number. What I did is I just kind of stapled these pages together, but you know how we were working with the geometry. So remember how we had the study skills? It's kind of, the paper is behind the study skills. So remember we had these strategies for academic success. Remember these study skills? These are like the decimal exercises in your Hawks learning. Well, this last page here is 21 here. Okay, and then after that came the geometry, and then we had customary measurements, like from the trapper keeper. Remember the trapper keeper days? And then this is what we need: the notation and terminology. Notation and terminology. You need to find that sheet. And then down here, it's types of numbers. And so they're talking about, on this problem, whole numbers are also integers. So these are your whole numbers. They start with 0. Think of, they use like a W, like for Wonder Woman. So this bold W. So whole numbers start with 0, 1, 2, 3, 4, 5. And then these ellipses, these 3 dots, continue on, 7, 8, 9. And they say that all whole numbers are also integers. They use for integers a bold Z. And these are your integers. You have some negatives, some positive numbers, and then 0. Okay. Notice how there are no decimals in here. Okay. And so that's true. It says all whole numbers are integers, because see these whole numbers right here, see, are also in this set, in this information right here. Okay. And so it's, you could say that whole numbers are a subset. They're a subset. They're inside the integer set. Okay. So that's why that's true. Excuse me. Okay. I'm sorry. So we have this bold W. Okay, that's whole numbers. Okay, and then I'm going to draw this up as a set: 0, 1, 2, 3, and so on and so on. So I have ellipses. And then I have this bold Z. Bold Z. Integers. Okay, so dot, 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 -2, -1, 0, 1, 2, 3, dot, dot, dot. Okay. And so I'm going to highlight these whole numbers and see how they are a subset. They're inside the set of integers. So I'm going to write that down somewhere. Whole numbers are a subset of integers. Okay. Also, the whole numbers and the integers are also real numbers. So numbers are either real or complex, like imaginary, like they have the eyes. None of these have little eyes, imaginary eye involved. So these are all real numbers. So I'm also going to say somewhere that the whole numbers and the integers are real numbers, not complex. And they use the bold R. They use the bold R. Okay. So if you've ever notice like advanced math textbook, like maybe a modern algebra textbook or a linear algebra textbook, you will see these references to these symbols often inside the books when they talk about the mathematics. Okay. Excuse me. Okay. So now, another vocabulary word that you want to put in here okay, let's talk about rational numbers first. Rational numbers, a number that can be written in the form a over b, like you can make it to a fraction, where a and b are integers, and you don't want b to be 0 because in math you can't divide by 0, it's undefined. Okay, but also we can say that rational numbers include the perfect roots. If you were to simplify a perfect root, what's left over after perfect root would be considered rational. You can always put that over 1, imagine 1, make it to a fraction. All terminating decimals would be an example of something that would be rational, and all repeating decimals also would be included. And also the integers, all the integers. See these integers, you can put all these over 1 and you've got like a fraction, like that idea that, like they said, a over b. Okay. So that's the extra definition for rational numbers. Now, irrational numbers, because a number is either rational or irrational, but it can't be both. So a number starts off as real or complex. Okay, can't be both. If it's complex, then you're done. You stop classifying. But if it's a real number, then you ask, is it rational or irrational? If it's irrational, then you're done. You stop. But if it's rational, then you continue, and then you ask, is it an integer? Is it a whole number? Is it a natural number? You keep trying to classify that and ask those questions. Okay. And then, the complex numbers have i's in them, and they say a plus bi, standard format. They have the imaginary part in them. Okay. So you do want to write those down. The irrational numbers, it says a number that can be written as an infinite, this is the word infinite, non-repeating decimal. Okay, and that's true, that's accurate. And also you want to include non-perfect roots, and you want to include the transcendental numbers, these are pi and e will be considered transcendental numbers, and they're irrational. Okay, so you want to write those down in your notes. Okay. Okay, so now we're going to go to page 19. And you can pause the video. You're still writing. You can pause the video, and that will let you write and get caught up with your writing. But otherwise, excuse me. Excuse me, I'm sorry. Otherwise, we need to look at page 19. Oh, I forgot that I always have to, because I have an answer key, I always kind of have to write the problems I'm gonna do. I always kind of have to write them out ahead of time. Sorry. We're gonna do mostly 7 and 8 on this page here. Okay, so they want us to, well, they have two classifications here, whole numbers and rational numbers. And we're going to list all these numbers in this set. They're called A, that are described in each exercise, whole numbers and rational. But we'll go ahead and also use this extra space around the paper to also classify, to use all the other types of numbers that pop up. Okay, so if I start analyzing this set A, this brace means this is the set A, all these numbers. Let me start out by saying that all these numbers are real numbers. All of set A are real numbers. Okay, then none of these have an I next to them. If one of them had an I or any of them had an I, then those would have to be called complex numbers. But none of these have an I, so they're all. It's safe to say that they're all real numbers. Okay, so now you got to further see if you can classify those real numbers. Okay, and so if I look at -7, okay. -7 is not a whole number. If you look at whole numbers right here, -7 is not a whole number. There's no negatives in that set there. And rational numbers, well, we can say that it's rational because -7 is an integer. If you look here at the integers, -7 would fall in here, -4, C dot, -5, -6, -7. -7 is an integer. And by definition, the rational numbers, when you evaluate those rational numbers, include perfect roots and terminology, decimals and repeating decimals and integers. So it can be classified for -7 as a rational number. And it's also an integer. So I'm going to put that here. And put -7 in there. Okay. So it's a real number. It's a rational number. And it's an integer. Okay. All right. This is -√6. Okay. I'm pretty sure when you evaluate that that's not going to be a perfect root. I think that's going to be a non-perfect root. So let me just show you. So the negative is down here. Square root, you want to hit the second key. And then the square root is right here. But you press this button, x². See? And then you're going to type in the number, which is 6. Oops, okay. So when that happens, I need to change the mode right here, mode. And I'm going to change it to classic. So I'm going to come down here and then hit enter. And I'm going to change it to classic instead of matte print. Okay, now when I go back and clear, and let me try that again. Negative second square root. So it's on top of the x squared, see that? Okay, and then it's a -6. Oh, it's a positive inside. Sorry, it's a +6 inside. I already put the negative outside. So let me delete that. Okay, whoops, I didn't want that column. Okay, let me see me clear. Okay, we start again. So negative second, and then the x squared, because on top you see that. Then just 6, and then close it. And I'm pretty sure you can get a decimal. Yeah, see you get that decimal? Okay, so that's a non-perfect root. So you go back to your vocabulary and see here under irrational numbers, infinite non-repeating decimal. And that means it includes the non-perfect roots as well as these transcendental numbers. Pi stems from 3.14, 22 divided by 7, 22 divided by 7. And that is a never-ending long division problem. It's infinite and non-repeating. Okay, so let's see. So we've got the non-perfect root. So it's going to be irrational. So I need to make a new one for irrational. I guess I'll put it right here. Okay, now we'll go to -2. And -2 is an integer. See, -2 is an integer. And it's also going to be a rational number. Rational numbers, see, are also integers. So -2 is a rational number. And it's also an integer. But that's about it, okay? Okay, now for the -5/3, you're going to want to change it to a decimal to see what it looks like. And when you set up like your long division, I'm going to set up my long division on the side here. It's the -5 goes inside the house. And the numerator goes inside the house. As this is -5 divided by 3. I'm going to pull up a decimal here and add some zeros. Let's add some zeros. Let's see what happens. So the answer is going to be negative here. And 3 goes into 5 about 1 time, because 3 times 1 is 3. Then we're going to subtract. And actually, I think what I'm going to do, because it's going to be confusing, I think I'm going to take this off. And it is negative, because you see it's -5/3. So it is negative. So I'll leave that there. But I'm going to take that negative off because you're just doing 5 minus 3. 5 minus 3 is 2. And then you're going to bring down the 0. And 3 goes into 20. This is where your multiplication charts are helpful. But let's try multiplication chart. Let's see. Where are my multiplication charts? I really need my multiplication charts. Where is it? can find yours, find yours. What can it be? Can't believe this. I'm sorry. I really need a multiplication chart. Is it? I had it earlier today. Cannot be very far. This is my desk is at home and this it can't be very far. I had it earlier today. I know because I need it because we're going to do some other problems where I know the number's not very big right now. There it is. I see one of them. I'm gonna take this one. I have a smaller one and the bigger one. I'm taking this one bigger one. All right. Sorry about that. Okay, let's see. So you want to say how many threes? No, yeah, how many threes go into 20? So what you do on the multiplication chart is you go to your threes here and you're looking for 20. 3 goes into 20 without going over. So see right here, 18. This is too big. 21 is too big, but here's 18. And you see right here is that 6. You're going to use the 6 that goes up in the quotient, your answer, and 6 times 3 is 18. So you're going to use the 6 and the 18 from your multiplication chart. Okay, so the 6 goes at the top in the quotient. Let's call your quotient. And then the 18 goes down here at the bottom. And 20 minus 18 is 2. Okay, so that's you've done a second cycle of long division. Okay, now I'm going to bring down the 0 again here. And this looks like it's repeating because you got 20 again. 3 goes into 20 about 6 times without going over. 3 times 6 is 18, and the remainder 20 minus 18 is 2. Okay, so actually I'm not going to use this 0 because that's enough for me to see that it's repeating. And the bar goes over that 1, 6, the set of numbers that repeat, which is just a lot of 6s. So this is actually equal to negative 1.6. So that's how you should write that. Like if you're going to use a bar, use it correctly, it just goes over 1/6. So this is how you should write that. Okay. And to show, you should check on your calculator. Negative 5 divided by 3. So the negative is down here. Negative 5 divided by 3. See, it's a repeating decimal. This is really a 6, but the computer program just rounds it off to terminate it. But it's really, it keeps repeating as 6s. Okay, so that's why I write it like that. And so now in your vocabulary, remember, repeating decimals, see down here, repeating decimals are also a form of rational numbers. Okay, so that's going to go under rational. But then that's it. It's a real number, it's a rational number, but then that's it. You cannot classify it anywhere else. Okay. Okay, then we have, that looks like negative 1.4. Is that right? Negative 1.4. That is a terminating. That's a terminating decimal. So terminating decimals are rational numbers as well. So I'm going to put that in here. And of of course, it's a real number. Okay. And it's also rational because it's terminating decimal. Okay, after negative 1.4, you have 0. Okay, so 0 is considered a rational number because 0 is an integer. If you look over here under integers, see 0 is in there. So rational numbers include integers, and so it is a rational number, and it's also an integer. So put that right here. Okay. And then I think we can continue besides an integer. 0 is, it's not a natural number, but it is, see, it is a whole number. It is a whole number. So you want that W in there. It's a whole number. So come over here. Okay, then we have 3/5. Okay, so I'm gonna have to make that into a decimal, inspect that. So the 3 goes inside the house, numerator goes inside the house, 3 divided by 5. Okay, and 5 doesn't go into 3, so I put a 0. But if I put a decimal, pull it up, it's 30. How many 5s go into 30 without going over? And I think it's exactly 6. 5 into 30, see? Exactly 6. 5 times 6 right there is 30. So that terminates, it's a terminating decimal, that's 0.6. And that's a terminating decimal. So if you look at your paper down here, rational numbers include also terminating decimals. So I'm going to put that under rational. I'm going to put the equivalent of 3/5 is what it was. But then that's it. That's it. Okay, you can't classify it as anything else. It's a real number and then rational. Okay, then we have square root of 5. Okay, and I think that's going to be a decimal, right? Use the calculator, second, and then the x squared key, see? And square root of, what was that? 5? See that long decimal? See that? So that's a non-perfect root. Non-perfect roots are going to be irrational numbers. So it's an irrational number right here. Irrational number is square root of 5. Also square root of 11 is going to be irrational also. Let me show you that. Second square root 11. See that? Non-perfect root. It's not a perfect root. It's a not perfect root. Excuse me. So non-perfect roots are irrational. Okay, next it looks like that's 4.5. Does that look like 4.5? No, it's 4 and then 5.9. Let me see if I can increase this. It's 4 comma and then it's 5.9 and then it's 8. Okay, so first we go with 4. So first let's look at 4. So 4 would be considered a rational number because 4 is an integer. See your integers right here? See that 4? So 4 is considered a rational number because it's considered an integer. Okay. And 4 is also going to be a whole number and an integer and a natural number. Wow, we haven't seen natural numbers. So 4 is also going to be, we said, we need the new natural numbers. Let me put this here, natural numbers, because we didn't have any. Four is an integer. I already have it there. Excuse me. Okay, I think I got all the place. Oh, and then the whole number. It's also a whole number. I think we covered all our bases there. Okay, 5.9. 5.9 is the next one. Let me increase it. 5.9, that's a terminating decimal. 5.9 is a terminating decimal. So terminating decimals are rational. Terminating decimals are rational. So I'm going to put a rational 5.9. But then that's it. That's it. It's real and then rational. Okay, then last but not least, we have 8. And 8 is considered a rational number because it's an integer. 8 is considered rational because it's considered an integer. So the number 8 would be under this list of integers. See that? 4, 5, 6, 7, 8. So I'm going to put 8 here. Excuse me, as an integer. I'm also going to put 8 here as a rational number. And 8 is also a whole number. See that? Whole number. And I think we already said it was an integer. Yeah, we already said it was an integer. But it's also a whole number. Okay, I think I got all of them. Let me just double check. Excuse me. Yeah, I can close this set. See, there was no more under rational. So there's no more, you can just close it. Okay. Okay, I think that looks accurate. Okay. Okay, let's see. Okay, now we're going to go to page 22. I'm so sorry. I'm not sure why I'm so sleepy. I don't know why. I think it's too quiet in here. Hurry up and finish. Fall asleep. I'm doing the recording. I'm looking for that page 22. I think it's on this side. Let me see. Okay, I'm looking for page 22. I know I had it before I was getting ready to record. I had it memorized. So I'll just pick that one page where let's see, here it is. There we go. Okay, so it looks like we're doing a few more classify -12. Okay, I'm also going to add a couple of others, F and G. I'm going to add real numbers, and I'm going to add the non-real complex number. And that's where, you have the involvement of A. It's a complex number, you have the involvement of A in it. So numbers start off as either real or non-real. So -12 starts off as a real number. And if it had an I, if it had been non-real, then you would have just stopped. You would have been done. It would have been non-real, you would have stopped. But since it's real, now you have to continue and ask yourself, well, okay, is it irrational or is it rational? Okay. And we're going to say that because it's an integer, -12, you see, is an integer. So integers are, rational numbers. Integers are rational numbers. So I'm going to say that I'm going to circle the rational number. And the reason would be because it's an integer and it's also an integer. Okay. But then that's it. Then you're done. Okay. Okay, now this next one, I'm also going to put, F and G. F is real. G is non-real complex number. Okay, now this number, I want you to notice it kind of has a pattern to it. Look how we have 10.47 and then look 447 and then 444, and we're guessing that the next one would be a 7 after that, and then probably 4 4s. And then probably another 7. And then probably more 4s, but an extra one. So 1, 2, 3, 4. So it'll be 5. And then I can, put ... which means it would continue on. Okay. So that is an example of a decimal that's considered infinite. Right here, see, infinite means it goes on and on and on. Infinite non-repeating decimal. Infinite non-repeating decimal. Okay. So that means that if we put that under infinite non-repeating decimal, that means we're looking at it being right here, irrational. Okay, irrational. And also it's going to be a real number. Okay. Excuse me. Okay, let's see. Sorry. Okay, let's see. Next. Okay. They want you to determine if this is true or false. And then if it's false, they want you to make it a true statement. Okay. Well, this, do y'all know that this little symbol means less than? And do you know that you always compare from left to right? You always compare from left to right. So when you look at this, any negative number is always going to be less than a positive. So this is actually going to be true. Okay. Now, to show your work that that's true, there's like 3 popular choices you can do. One of them is called cross products. To -1/3, 4/3. Okay. So here the order is important. Here, when you're doing your multiplication for this, you've got to go this route. Okay, and that means that -1 times 3 is -3. Okay, and then when you do the other side, the other cross product, the other side, 4 times 3 is 12. So you're comparing now -3 with 12. And -3 is something that's less than 12. That's a symbol for that. Okay. All right. Now if I'm going to show you another way in case you're not interested in the cross products, there is another method, which is to do long division. When you do long division, remember we said the numerator, the top number goes inside the house. So this -1, I'm going to put 1 divided by 3. And I'm going to put the negative up here because it's negative. And I'm also going to put decimal here and some zeros. So I'm going to say how many 3s go into 1? And you would say none. If you were a size 3 shoe, you couldn't fit that foot into a size 1 shoe. So -3 doesn't go into 1, so it's 0. But you can ask how many 3s go into 10. Okay, remember this decimal got pulled up. So really this is just 10, 1 0. And 3 times 3 is 9. And 10 minus 9. 10 minus 9. Let me just take this off and put a decimal guide. 10 take away 9 is 1. Okay, then you add a 0 and pull it down. And 3 goes into 10. 3 times 3 is 9. 10 minus 9, excuse me, is 1. Okay. All right, so now I'm going to get my calculator and I'm going to just double check that. -1 divided by 3. -1 divided by 3 is, see, -3 repeating. So see, that is what we have. We have -0.3 and then the bar over that digit that keeps repeating. Okay. And then if we do long division on the other side, 4 divided by 3, the numerator goes inside the house, then add a 0, pull up your decimal. So 3 goes into 4 one time. 3 times 1 is 3. 4 minus 3 is 1. Then bring down 0. 3 goes into 10 about 3 times. 3 times 3 is 9. And 10 minus 9 is 1. Okay. And if we do it, continue one more time, just make sure, see what we see, add a 0 here, pull it down. 3 goes into 10 about 3 times. 3 times 3 is 9. 1 left over. Okay, so I'm going to check that on my calculator. I'm going to do 4 divided by 3 on my calculator. 4 divided by 3. And you see how we do get a repeating decimal. So this equals positive 1.3 with the bar over that, okay? And there is a third method. Third method is you want to find a common denominator and build up the fractions, and then you just compare the numerators. The good thing about this problem, part 3, is that you already have common denominators, so you don't have to build them up. You're just going to compare it. So I'm going to say use common denominators and compare using numerators. Compare using numerators. Okay, so for us, that we already have a denominator both common of 3. So you just compare the numerators, and -1 in comparison to 4. Well, -1 is less than. And I wrote the wrong, it's -1 is less than 4, but I didn't write the right symbol because I think I dozing off. I'm sorry. So it's less than. This is the symbol we want. Sorry about that. Less than. Okay. All right. And let's see. The other thing I was going to say about this one is that when you compare these, -0.3 is what in comparison to 1.3. So yes, it's less than. Okay. But with either of the 3 methods, you end up with similar thinking, which is that this is true, that this less than symbol is true. It's just, there's just a little variation on how you can show that work. Okay. Okay, let's go to the next page. Let's go, that was 22. Let's go to 23. So the other thing I was going to say is that when we take our tests, you definitely will have a problem like this, but either they're going to both be negatives, 2 negative fractions, or they're both going to be positives. But you will have something like this where you have to, if you're going to show your work by finding the size of these fractions, you've got to be familiar with your app, your student Canvas app. Let's see. Yeah, because I was talking about that you're going to have one like this on the test, but it won't be a negative and a positive. It'll either be two negatives or two positives. But you want to be able to show your work using a method. So remember to use either cross products or just plain long division, or to build up your fraction by finding a common denominator, then building it up and then comparing, okay? Okay, let's look at 23, page 23. And it looks like they want us to compare the number 6 divided by 19. Okay, so I'm going to set it up here. Okay, so 19 won't go into 6, but how many 19s go into 60? So let's see. 19 into 60. Into 60. Get how close can I get to 60 without going? It looks like right here. Looks like that's 57. So if I go up to the top, that's 3. Or you count here, 1, 2, 3. So in your quotient, you're going to write 3, and then you're going to write 57 under the subtraction part. And then you're going to subtract 60 minus 57 is just 3. And you're going to keep going. You can add a 0, pull it down. And how many 19s go into 30? Probably just 1, because I think if you do 2, yeah, I think if you do 2, it's too big. It looks like if you do 2, it looks like it's going to be 38. And you don't want to go over. So we're going to do 1. 19 times 1 is 19. And then we're going to have to do a little borrowing. You can't do 0 take away 9. So you have to like borrow from the 3, make it 2. Make this 0 10. And 10 minus 9 is 1. 2 minus 1 is 1. Okay. And so it looks like it's going to keep going. I'm going to add another 0, pull it down. And now I want to see how many 19s go into 110 without going over. If I go back to 19, and I get as close as I can to 110 without going over, which should be about right here. That would be 95. So 1, 2, 3, 4, 5. But go to 5, I get 95. 19 times 5 is 95. Okay, and then if I do a little subtraction, make this a 10, decrease this 1, make it a 0. So 10 minus 5 is 5. Okay, and then I can't do 0 minus 9, so I have to borrow again. Then I make this 0 into a 10. 10 minus 9 is 1. So it looks like it's a remainder of 15. And it looks like it's going to keep going because it doesn't terminate on the remainder of 0. So I'm going to use my calculator at this point now, because once you've demonstrated that you can do long division repetitively over and over, and it's correct with one, when you check your, once you've done 3 long divisions like these cycles, that's enough to show that you demonstrate that you understand how to do long division, how to compute it. So then I'm going to use my calculator to do 6 divided by 19. You see that long decimal? So see how we got the 315, and then they're saying 7, 8, 9, 4, 7, 4. Okay, and that's going to be an example of infinite, non-repeating decimal. Yeah, so if you go back to this, see, infinite and non-repeating decimal, that'd be an example of an irrational number. Irrational number. So this is going to be an irrational number. And I'm also going to put that it's a real number. Not complex, or it doesn't have the I in there, okay? All right. Okay, one more problem like that. I think this is the last classified. Square root of 5. Okay, I think have we done that before? That looks like that's gonna be a decimal. If I do second and then the x squared key. That pulls up your radical, and then you want to type the 5. Then I'm going to close it. And there it is. It's a decimal. 2.23606.978. And that is, it's a non, that's what they call, this is what they call a non perfect root. So non-perfect roots are right here, see? Non-perfect roots. Those are irrational numbers. And then it's going to be still a real number. Okay. Use some pause. Okay, let's go to 24. So they want you to plot the numbers on a number line. Okay, what I'm going to go and do is I'm going to include some decimals just so you can, so I can practice and ask you some questions with some values that have decimals in them. So I'm going to start about right here. Put the number 0 there, and then I'm going to make this tick mark negative 0.5, and then this would be negative 1, negative 1. This would be negative 1.5. This would be negative 2, negative 2.5, negative 3, negative 3.5, excuse me, negative 4, negative 4.5, negative 5, to 5.5. Okay, on the other side, instead of 0, I have 0.5. 1.5. Okay. All right, I think that's fine. Okay, now, if we wanted to identify or plot negative 1.7, would you be able to do that? So negative 1.5 is right here, and then negative 1.7 is between negative 1.5 and negative 2 in there. So what happens is, like, there's these little tick marks. Okay. And so after negative 1.5 would be negative 1.6. Then after negative 1.6 be negative 1.7. Then after that would be negative 1.8. So negative 1.6, negative 1.7, negative 1.8, negative 1.9. And then you get back to, I'm sorry. So you have negative 1.5, negative 1.6, negative 1.7, negative 1.8, and then negative 1.9. And then you would hit negative 2, right? So that's kind of what happens in this little space here between negative 1.5 and negative 2. You have negative 1.6, negative 1.7, negative 1.8, negative 1.9, and then 2. So I hope that helps you with that idea there. And so if I wanted to plot negative 1.7, we could say it would be about, maybe about right here. Right there, okay? And then the other numbers are easier to plot. Like they want you to plot negative 5 and negative 3, negative 2, and then 3. So I did take this out long enough, but if we want 3, this would be 2, 2.5. Okay. All right, so I'm plotting negative 5, negative 3, negative 2, and then 3. Okay, now if I were to ask you to compare negative 5 with negative 2, okay? Remember, we always have to compare from left to right. So you're saying negative 5 is what in comparison to negative 2? Well, if you look where they're at, negative 5, negative 2, and remember that comment that we learned when we first started the lesson? Remember, it said smaller numbers are always to the left of larger numbers. So we look at these, the -5 and the -2. This is going to be the smaller number. This is to the left of the trash can, right to the left of that little space there. So -5 is smaller. So that's what we want to do, is we want to write the correct inequality for that. And that would be this. Okay, that means it's less than. Now, what I also could do is use these same two numbers, but just put it in a different order. See, these are basically the two numbers that we just used, but I switched the position. So the notes say when you're comparing, when you're applying these, you're comparing them. You're comparing them means from left to right. So -2 still here, -5 is still here, but now this is smaller. So this is the less than. So -2 is going to be -2 is going to be greater than -5. Okay, so I can actually leave this off. Just say it's greater than. -2 is greater than 5. Okay. Okay. Now on number 7, they want you to graph the following set of integers on a real number line, all positive integers greater than 2. Okay, so I'm gonna go ahead and draw a little number line. I'll just start 0 here, 0. Okay, so I don't think we have to label each tick mark, but just enough to get us through this problem. Let's see. They want you to graph all the positive integers that are greater than 5. Okay, so these numbers that are greater than 5. So remember what integers are. Remember definition of integers, just right here. This is what the integers look like. So identify which the following set of integers on the line. So positive integers greater than 5. Okay, so we want to shade to the right. Shade to the right of 5, greater than 5, and don't include the 5. It is a greater that or equal to. It is a greater than. So don't include the 5. So on the computer, okay, first of all, you're gonna get your mouse, pick up your mouse, and do this. 5, 6, 7, 8, 9, so on and so on. And on the computer, you're going to have to click on the infinity. And when you click on the infinity, it's to let you know that other numbers beyond 5 are also part of the answer. So it's going to the infinity symbol. So you want to, on the computer, you want to click on the infinity to include the other integers. that exists beyond 5. So you want to like literally go to this infinity. And when you click on that infinity symbol, what will happen is these 3 ellipses will appear. Okay, which means that includes, highlights all the numbers that are like they want greater than 5, the whole numbers and whatnot that are greater than 5, all the numbers that are greater than 5. Okay. I'm sorry. Let's see. Did I doze off again? I'm sorry. I'm gonna have to record a little bit earlier than so that doesn't happen again. I'm sorry. Let's see. This is also called negative infinity. But you don't want to click on that. If you click on that, then you're saying that you want to include numbers, on the negative side to the left of that, and you don't. You want the positives. Okay, I think we just have 2 more pages. Let's see if I can finish. No, I think it's 3 pages. No, 2 pages. Let's see if I can finish 2 without dozing off again. I'm sorry. Okay. Here we go. Page 25. All right, now you're gonna need, you're gonna have to go back to these sheets, and we need a new sheet. So you need a new sheet. So you're going past the formulas and theorems, past the principles of properties. Although I'm noticing something, even though I'm very sleepy, I'm noticing something here. You know how in our co-rec course, the first 2 co-rec lessons we did, this is actually helpful to reference to that, look for your co-rec. And you can use this sheet while you take the quiz. So you can have this sheet out when you take the quiz. And also, I just didn't notice it before until today when I was going through the notes and everything. So you're welcome to use that, and it does have little hints about some of the properties we've done in the 1.5. I guess it's 1.2 and 1.3. I think those first few lessons of the co-rec. Yeah, but we need to go though for our problem. Our problem. See this? See these right here? Those are absolute values, and then you see this. That's an equation. So what we're doing is we're doing absolute value inequalities. That's what we're doing. Absolute. Oh no, not inequalities, equations. This is an equation. Sorry, absolute value equations. Okay. All right. Now, when you look at this sheet, it's called equations and inequalities. I want you to notice down here, see how it says absolute value equations? Okay, so you see your choices here. And it says for the statements 1 and 2, for both of these statements, that C has to be greater than 0. Okay. And then you want to look for something very similar to this, absolute value of x equals 104. And I would say number 1, when I look at all of them, number 1 would be closest to that look. Because let's see, it looks very similar. See, absolute value of x equals C. Okay, so you got your C is like your 10.4. There's your absolute value of that. Okay, and so I'm going to write that down on this paper here. Let me write that down on this paper here. It's going to say C is greater than 0. So if absolute value of x equals C, then x equals C or x equals negative C. Okay, so that's saying that for us, the C, in order to fall in this formula, your C would have to be greater than 0. And it is, for us, it's 10.4. And if that's the case, then you're trying to think what answers would make that true. They're saying that you would use C and negative C. So for us, our answer is going to be x equals 10.4 or x equals negative 10.4. Okay. And also sometimes you can write the answers in sets like this. So 10.4 and negative 10.4. Now, if you wanted to do a check, let's see, to be braces. Now, those would be your answers that work. So what you're trying to do is find numbers that you can substitute in for x and make a true statement. And if we do a check to show that absolute value of x, so we let x be 10.4 first off. And we're like, okay, what if we let x be 10.4? What will that equal? Well, what is the absolute value of 10.4? It's just 10.4. And you see, that's what they need. So this is one of your answers. Then let's also do the other check. What if we let it be negative 10.4? Okay. Well, the absolute value of a negative 10.4 is 10.4. Okay. And so these are good checks that gives you true statements. So this is our answer. Okay. And again, that's because it follows best this module. When you look at all the modules, like there's 4 of them descriptions, this is the best one that meets that. So if absolute value of x is equal to 0, is equal to C, then your answers are C and negative C. So you're negating the C, and then it's negate. Now, if somebody were to say, well, I want my answer to be, I want to say that my answer here, I want to include 5. Well, if you do it, if you do a check for that, using 5, you have your absolute value x, and you let x be 5. So you're checking for 5. So you're going to put 5 inside that and then see what that gives you. Is that going to give you 10.4? I don't think so. No. Okay. So the absolute value of 5 is 5, but you needed 10.4. Okay. So charge. Okay. Now I need to show you this one. Absolute value of x equals negative 12.3. So you remember that I told you that the only way when you work with absolute values that it could end up being negative would be that if you had the negative also, out here. Remember I mentioned that? Okay. So it turns out that for this problem, it's not logical. When you take the absolute value of a real number, you're supposed to get back, it's a distance. So you're supposed to get back something positive. It's a distance. So it couldn't be negative. There's something wrong with that. It's illogical. And I don't see on here. Excuse me, I don't think I'm ready. I'm trying to look for that on here. I don't think you really need that. Could be okay without that, but I was going to say that I'm going to say this absolute value is a distance from 0. Absolute value is a distance from 0. And remember that distance is not negative. So this couldn't be a possibility. This couldn't happen. You can't be, distance cannot be negative. So that means that as far as our answer goes, we have what they call no solution. Put the empty set. Empty set, empty set. Yeah, so for number 9, your answer is going to be no solution. And another way to say that is to write a 0 with a slash through it. And if you've ever had a math teacher ask you to please not write your zeros like that, it's because it means something else. It means priority, it means empty set, no solution. Okay. And then you could have like right with braces except nothing inside it. And then you have that comment there, empty set. Okay. All right. Let's look at 10. Determine the value on the left if the value on the left is less than, greater than, or equal to the value on the right. Okay, this one has like 3 parts to it. First, I would say part 1 is you want to determine what is this result. Okay, see how it has a negative outside of the bars? That's the only time that can be negative, should be negative. And the absolute value of -4 is just 4. And then you have part 2. What is the absolute value of -10? And that's just 10. Okay. And now we're comparing the notes for looking and comparing -4 to 10 now. -4 to 10. -4 is what in comparison to 10? It's less than. So you always compare from left to right, always. So the symbol for less than would be this. Okay. All right, I think got everything. Is that it? And I was going to draw a number line too to show you. Here's 0 just to give you a little orientation, and 10 is somewhere way over here, and the -4 is somewhere here. But I put little bullets on those numbers there. It also shows you that, yeah, -4 is less than 10. Okay, and then this one's got the negative outside of the bar, so it uses vocabulary. This one doesn't have the negative outside of the bars. It's just less than. Okay, I think I'm done. Sorry about that. Sorry about that by dozing off a little bit. Oh no, there's one more page. Oh goodness, let's see. 26. Okay. So I can, okay, that's 2 more problems. Okay, so determine the statement is true or false. If it's false, rewrite it to a form that makes it true. Okay. Okay, so part 1 is you definitely have to compute that absolute value. Absolute value of -2 is 2. So you basically have 5/2 is greater than 2. Everybody needs to be, doing that. Anytime you have absolute value, you just got to simplify it. And then you can look at it with fresh eyes. And how do you want to compare it? If you want to compare it by doing cross products, that would be an option. And then it goes, the order is important. You have to go this way. So you're multiplying 5 times 1, which is 5. And then on the other side, then you're comparing 2 times 2, right? So you're doing this cross multiply here, and then you're doing this here. And you end up with, when you do your cross products, you end up with comparing, oh, and this is a 3. Is that a 3? Sorry, that's a 3. So it's 5 over 3. So I'm doing class 5 times 1. So yes, goes this way. Yeah. So I'm doing 5 times 1, which is 5. And then I'm going this direction. So that would be 2 times 3, which is actually 6. So now you can compare 5 is what in comparison to 6. 5 is less than. So that's your symbol. Okay. Now, so one method is to do cross products. The other method is to just do long division. So you have the 5. It's important to set it up correctly. The 5 goes inside the house. Make this a 10, you have to borrow, decrease this. 10 minus 8, 4 minus 1 is 3. And then I'm going to add a 0, pull it down. And let's see. That looks like I have an error there. What happened? Let me start again. I'm sorry. Doing long division. 5 divided by 3. Okay, so the numerator goes inside the house. Okay, so 3 goes into 5 one time. 3 times 1 is 3. 5 minus 3 is 2. Okay, add a decimal, pull it up, add a 0, bring it down, and you have 20. 3 goes into 20 without going over. So let's see. 3 into 20 without going over. That's about right here, right? 18. 3 times 6 is 18. So 3 times 6 is 18. So the 6 goes at the top and the 18 goes at the bottom. 20 minus 18 is 2. Okay, then add another 0, pull it down, and it looks like it's going to be repeating. 3 goes into that about 6 times. 2 left over. Now I use my calculator to double check. 5 divided by 3. See all that repeating sixes then? So this is 1.6 with a bar over that. Okay. So that's the value of the 5/3. It's about 1.6 with a bar over that. And then 2, you don't need to do long division on 2. 2 is just 2. You know, it's not like set up like a fraction like this where you have to do long division. It's already a whole number 2. And 1.6 is what in comparison to 2? 1.6 is less than. So it should be going this way. So that means that this is false then, right? It means that that's false. And what was the third? Do you remember what was the third method? Remember I showed you 3 methods in that other problem earlier? It was cross products or just relying on long division to show your work. Because when you take your test, you're going to have a problem like this, where you're comparing like 2 fractions. Is it less than, greater than, or equal to? But you have to show your work. So you either do cross products. And with the cross products, you just have to be careful because, the order, you have to do this order. It's important. This is 5 times 1 and then 2 times 3. So sometimes students get it wrong because they do the cross products in a different order. You definitely have to have the 5 times 1, start off with that product, okay? So it's cross products or long division. Or the other one is to find a common denominator. So where can I show that? At the top. So you have 5/3, and you're comparing that with 2/1. And if you're trying to find a common, see how these are not common denominators, 3 and 1. If you're trying to find common denominators, I always use multiples of the denominators. So like for 3, if I look at multiples, 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. These are multiples. 3, 6, 9. And then for the 1, 1 times 1 is 1. 1 times 2 is 2. 1 times 3 is 3. 1 times 4 is 4. So I have 1, 2, 3, 4. And then you see right here how you have a match. See here on 3 how you have a match. That's your least common multiple, which is also your least common denominator, which is going to be 3. So when you build up your fraction, this is already good. This is already 5/3. But this one you're going to have to build up. And you're going to have to build it up by multiplying it by how many multiples did you need of 1 to get to the LCM of 3. So you just go back here and count on the ones. 1, 2, 3. So you needed 3, so you're going to multiply this by 3. Okay, so now you have 2 times 3, which is 6, and 1 times 3, which is 3. And on this side stayed the same because it was already 3. So that now look, now you have common denominators. So now you can just compare the numerators. And when you compare the numerators, you have 5 compared with 6. So 5 is what in comparison to 6? 5 is less than. It's less than. Okay. All right. So I hope that helps then. Okay. And I have one more problem. plot the set of integers indicated by the inequality. And this is an inequality. The absolute value of A is greater than 4. Okay, I'm looking for, I need to go back to my little notes here with these. And we're doing this absolute value inequalities. This is for C greater than 0. And I believe our C is already, see, it's 4. It's already greater than 0, so we're good. And if I look at all these choices, you can see how I put a little star on this one. This is closest to our form than the other ones. Absolute value of X is greater than C. So don't worry about the uses of X's and A's. The book here used an A and this is uses an X. So they're variables. So don't let that worry you. That's still okay. Absolute value of X is greater than C. See, we have that. And then this is going to happen. It's kind of going both ways like that. Either X is less than negative C or X is greater than C. So let me write that down. If absolute value of X is greater than C, then X is less than negative C or X is greater than C. And these are absolute value inequalities. Absolute value, but inequality. Absolute value inequality. And so for us, this is like our C, which is 4. And also in your book, it does say that for C is greater than 0. It starts off with that. It's important. And our C is greater than 0 is 4. So if C is greater than 0, it fits best into this formula, very similar to that. And this is what our output is. That means for us, that means that we have X is less than negative 4. So we have, or that X is greater than 4. And that's what we have, interpret. So that's why I was going both ways. Okay. So kind of what that means in a number line. So here's 0, here's negative 4, here's 4. And we have these parentheses here. And I have all this shaded. And the thing is that this includes, when you do all this shading, this includes integers as well as like the little fractions and the decimals. Your problem is limited to only the integers, So I number my number line, let's see, 0. Number your number line. Okay. And if you're wondering why parentheses and not brackets, if I had brackets, then we would have had something like this. Absolute value A is greater than or equal to 4. You would have had to have this, I call it an underscore. And I have a bracket on that. And then everything was shaded this way. So if it had this little underscore, then I would have used the bracket on, you know, the direction that we're shading. But since it doesn't here, this is using parentheses. Okay. And for us, we're narrowing it down to just the inequality, just the integers. So what we want is starting with 5, 5, 6, 7, 8, 9, 10. And then so on and so on, like 11, and then 12. And then you want to click on the infinity with your mouse. And when you click on that infinity, then these 3 dots open up. Okay. All right. So let's see. What else can I say about that side? Anything else? What else can I say? Greater than 4. Greater than 4 is like starting with 5. Okay. You want just the integers. You don't see, because when you shade everything in between, you're even, you know, counting those little decimals and fractions that are in between those, and we don't want that because they just set the integers. Okay, but this is still applicable, you know, that you're going opposite directions. And then this is parentheses, this is bracket. That's important. Okay, so now we need to go on the other side to talk about this side. X is less than -4. So here's -4. So we're looking at -5, 6, and so on and so on. Okay. And then, and then for the same reason here, you would click on the negative infinity with the mouse. And when you do that, these little dots are going to appear at the top. Okay. All right, that was tough. Okay, I think I got them all in, and I apologize for dozing off on some of those problems. And I need to just record myself earlier. I record myself too late, and I get sleepy, and it's so quiet that I kind of doze off. So I apologize for that, and then I'll try to get the recordings done earlier. Okay, I'm pretty sure I did them correctly. You know, after I caught that. It's probably a little comical for you to see. So sorry about that. Okay. Okay. Have a good one. Bye-bye.